Let me just share my screen then. Did that work? Excellent, cool. I've left some time at the end for some questions, but if anyone wants to interrupt me and ask questions while I'm going, feel free. I'm not sure I'll notice if it happens in the chat, but like turn your microphone on and interrupt me, that's fine. I have no problems with that. So yeah, I'm Rose Fennick. I'm studying at the University of Leicester. I'm in my 4th year of my PhD, so I'm just about to start writing my thesis. I'm studying machine learning for Earth observation and focusing on the retrieval of methane from satellite data. I'm studying under Professor Ivan Chukin and Professor Hartmut Bosch, who are in the maths department and the physics department, respectively. So I'll start by talking about the greenhouse effect, why it's important, some kind of misconceptions about it. And then I'll talk a little bit about the satellite that we use in the data. And then I'll talk a little bit about the methodology, the neural network solution, that kind of thing, and a few of the challenges that I've faced throughout my project. And then finally, I'll present some of the results from the various steps that I've talked about. So first, the greenhouse effect. I think we all have heard of the greenhouse effect, but I'm not sure everyone really understands what it is and why we're worried about it, and what it is that we're worried about. So it's a very basic explanation. What happens is that the sun's radiation comes towards the Earth. The Earth absorbs some of that energy, some of it's reflected back into the atmosphere, but the Earth absorbs the majority of it. Then the Earth kind of emits some heat back into space. Some of it just goes straight through the atmosphere, no problems, but greenhouse gases trap most of it, which keeps the planet warm. So as the greenhouse effect is nothing to worry about. We need it. Without the greenhouse effect, it would be like 0 degrees Fahrenheit or something on Earth, which I wouldn't want to live in. I don't know about you, but so the greenhouse effect itself isn't anything to worry about. The thing that we worry about is that the amount of greenhouse gases is increasing, and so the warming effect is increasing. So the worry is that the increase in the greenhouse effect rather than the greenhouse effect itself. But what are the greenhouse gases? So we've all heard about the famous one, carbon dioxide, which makes up 82% of greenhouse gas emissions, followed by 10% from methane, and then some smaller emissions from water vapor, nitrous oxide, ozone, and CFCs. So yeah, that's the picture of greenhouse gases. So you might be wondering why I would focus on methane rather than carbon dioxide if carbon dioxide is the big one on that pie chart. So obviously we all know about carbon dioxide. There's a lot of research in it, which is one of the reasons that I would focus on another gas. The other thing is that carbon dioxide has a much longer lifetime in the atmosphere. So it's hundreds of years compared to just kind of 12.5 for methane, which means that you've got a kind of smaller window to deal with it. It also accounts for 20% of the global warming effect, even though it's only 10% of those greenhouse gas emissions. So it's far more potent than carbon dioxide. So it's having a much stronger effect. And on top of that, 70% of it is anthropogenic, which means that it's man-made. So 70% of that methane comes from human activity, which means that human activities accounts for most of that 20% of the global warming effect. So where does methane come from? So it doesn't all come from cow farts. In fact, it's cow burps, not farts. So correct all of your friends about that misconception. But most of the anthropogenic stuff comes from fossil fuel production and use and agriculture. There's a little bit of biomass and biofuel burning as well, which is both natural and anthropogenic, and then naturally occurring through wetlands, inland waters, some vegetation, and certain wild animals. as cows. So we also have a few sinks. They're all natural sinks, so that's absorption of methane, so it doesn't get emitted. But as you can see from this plot, a lot of it comes from people. So that's methane. That's why it's important, and that's why we want to know more about it and work to find the emissions globally. So the Sentinel-5 Precursor satellite is where I got all my data from. It's what I work with. It was launched at the end of 2017. We don't have any data from it until I think April 2018. So there's a kind of 6-month validation window where they check out what's going on, calibrate things, that kind of thing. So we've got a lot of data from April 2018 till probably April 2021. I haven't checked the most recent data. On board that is the tropospheric monitoring instrument, which is what records all the information that we need. It orbits the Earth around 14.5 times a day, which is a lot, and gives us near global coverage. So every day we're getting almost a complete picture of the Earth. But that generates masses of data. I think it's about 1 terabyte a day of raw data. Obviously that's processed and we lose some of it, but that's massive. At the moment, they use a forward model to get methane from this data. This image here is the basic forward model as it's presented in the documentation. As you can see, it's not that basic. There's quite a lot of ins and outs and little steps going on that all interrelate a little bit. They also have to do some processing, and there's a little bit of extra inferred data included in there, which doesn't come from the satellite. There's some steps to the calculations. And then on top of this, they bias correct their results to get a more accurate picture. There's some ground monitoring systems which give us accurate methane data, which they calibrate all the results from. So that's the system, which, as you can see, is a little bit convoluted and quite slow. So sometimes it can take months to get a methane concentration from data that went in a long time ago. Obviously, anyone can take the data and calculate the methane themselves following this process, but the official product isn't often released for weeks, months after the data is downloaded. So that's where my project comes in, and looking at a neural network solution. So why would we use machine learning and neural network solution for this problem? So firstly, we've got this massive amount of data. So we know that machine learning is something that is very good with dealing with large amounts of data. We hope that by training a model using the bias corrected data, we can have the network infer the extra data that would have been put in that's done from calculations, and also do the bias correction step as part of the network, because it knows that the bias corrected data is its output. So that's a really great benefit. It takes away some of the steps. It will be much faster in the long run. And potentially, if you could build a small enough network, there's a potential for a low memory onboard solution. So you could put this a Raspberry Pi or similar onto the satellite, and it could potentially get us some relatively accurate methane concentrations in near real time. Even if they weren't, perfectly accurate, it would still give us indications of increases and that kind of thing much quicker than we get now. So my methodology starts with standardizing the data, which is a really important step, because in this case, I have approximately 1,800 features, which is massive. Most of those come from the spectral data that the satellite records. But we also have latitude and longitude. There's a few things like solar zenith angle, which is to do with the angle of the sun, that kind of thing. And they're all on different scales. So you've got wavelength there, which is between 2,300 and 2,400 nanometers. And then you've got latitude and longitude, which are kind of in the low hundreds. So these different ranges. can cause the network some problems or add some steps to the network. So standardizing just brings everything to the same scale, and it means that you don't accidentally give more importance to one feature over another just by the fact that it's on a different scale. So the way we do that is we take each point, we subtract the mean of that feature and divide by the standard deviation of that feature, and that should put them onto closer scales. The next thing that I've implemented, although the results I'll show you later don't include this step because I haven't yet got final results from this, is dimension reduction. So we can use principal component analysis to reduce our dimensions. So as I say, we have 1,800 features, which is a lot of features. And a lot of those might be quite closely linked. So what principal component analysis does is it takes our data, I give it quite a large sample of my data, and it analyzes that, and it creates 1,800 new features, each of which are linear combinations of the old features. So that means that in theory, a smaller number of these new features would explain the variation in the data as well, or as close to as well, as using all 1,800 features, which means we can reduce the data right down without losing too much of the variation in the data itself. This means that we obviously are looking at a much smaller data set when I've got millions of rows of data and then 1,800 features or columns in my data set. So by reducing that 1,800 down, we're quite significantly reducing the data that we have to play with. We could then train using these new principal components. That is the step that I haven't yet done. So the rest of, I'll show you some of the results from my principal component analysis, but the results that I'll share of my network don't include this step yet, but I'm hoping that that will improve my results somewhat. So the neural network itself that I have used and that I have trained on relatively successfully, used about 430,000 data points in its training set. I have a lot more data than that now. At the time that I did this piece of work, that was about all the data I had. I had a much smaller window of data. I think it was about 6 months worth of data, whereas now I have more like 2 years. And I'd filtered out a lot of things that I maybe don't filter anymore. But I'm now looking at kind of more like 2-3 million points. My test set was a little bit smaller, so about 180,000 data points. My inputs included spectral data, which I'll talk about a little bit in a minute, and then a few satellite calibration bits of information, so solar zenith angle, that kind of thing, which were found in the one or two other similar pieces of work were found to improve the results significantly. So that's why I've included those. The target for my network was the Esron bias corrected CH4 mixing ratio, which is the name of the concentration of methane in the atmosphere. Esron is, I believe, the space agency in the Netherlands, but they provide this product. The network had 2 hidden layers, each with 128 and 256 nodes. And I ran it over 2,500 epochs, which was quite a lot. And I haven't included a training curve in here. I perhaps should have, but I could see from that the training could have been continued further to potentially improve the results. Just quickly, before I move on to some of my results, I'll talk about some of the issues and challenges that I faced. One of them being that, at least when I started 4 years ago, there wasn't, within the Earth observation space, there's not a lot of machine learning going on. They're a bit skeptical of it. They're interested in doing it, but they're skeptical. So there's not a lot of similar work going on. There's a little bit with carbon dioxide. I could only find 1 or 2 papers to kind of reference to. So a lot of what I've had to do has been almost completely from scratch because there's not really a precedent for it. Which is really interesting, but obviously means that I am starting from scratch, and every decision I have to think about. So the number of hidden nodes, hidden layers and nodes. I did lots of experimentation to get to get those different hyperparameters set in the end. Also, computationally, massive amount of data. I use the HPC at the university, which is great, but that comes with its own challenges, queuing systems, service days, crashing at the weekend, that kind of thing. So yeah, it hasn't been without challenges, but this is where we're at. So I'll go through some results now. I'll start by showing you what the data I have looks like. This is the coverage we get. So there are some missing points. Part of that is to do with the data that I had available at the time. So this, I don't know if you can see my mouse, but there's sections in the middle kind of stripe that are missing that seems to be to do with the data that I selected to train with for various reasons. I'm hoping that now I have a much larger data set covering a wider time frame, some of those gaps will be filled in. You can see that there aren't many of those very low points, but there's not much below 1700. A lot of that gets filtered out because it's down the bottom here and is, in the words of one of my supervisors, not that interesting. So that's why you can't see much of those points on there. The interesting points tend to be the more extreme values, the darker orange and red points, because they're the extremes. They're the interesting points. That's where we might have plumes of methane or larger emissions for various reasons. But they're the interesting points. So it is important that those points in particular are predicted well, because that's what the focus of the scientist is. You know, if it's in the normal range, we don't really need to do that much, whereas the scientists want to know the extreme places. So this is the spectrum, and this represents the majority of my input data. I don't input it as a spectrum, but this is what it would look like plotted. So on the left we have the standard spectrum. That's almost completely raw from the satellite. For one point, it's a good point. I filtered out all the bad points, so there is some filtering, and a little bit of processing, but essentially that's what the satellite gives us, that spectrum. On the right, I have the log of the spectrum, which is what I will be using going forward as an input to my network. The results that you see today use the left-hand side, but on the right-hand side, we'll be using the log of the spectrum, because the relationship between the radiance and methane concentration is closer to a log relationship than a linear relationship. So it just makes sense, and I'll be doing some experiments to check that that is the case. But you can see that we can still see the pattern. It looks very similar, left and right. They're just some of the troughs are slightly elongated, and the peaks are, that large peak is squished a little bit, but it shouldn't have a major effect, I hope. So let's talk about the PCA. So before I show you the results that I have, I will discuss the principal component analysis and the results from that. So as I said, we started with 1800 features. We then got our new 1800 new features with the linear relationships or linear combinations of the others. Here I've plotted 45, I think, maybe 46, because then it just becomes a flat line of 1800 and you lose that kind of information at the beginning of this plot. So what we can see from this is that just one principal component explains the variation of the data, or 52% of the variation in the data. Interestingly, that principal component is a linear combination of all of the inputs except for a lot of the spectral data. I think only 1 or 2 spectral points were included in that, which is interesting because it means that you can get a lot of the variance in the data comes from that point. It's important to note that variance in the data refers to the input data and not the methane. So it doesn't necessarily mean that first principal component will be 52% accurate or anything like that. Just that the variation in that input data is explained, or 52% of it is explained by that first principal component. We then go up to 3 principal components and we get 98.91% the variance, which is pretty good. It should be enough. On most occasions, that would be enough of the variance. And I'll be doing some experiments in the coming weeks and months to look at whether the difference between 3, 10, 20, and that 38, where you get to 99.95% of the variance, which is as much as you can explain with the linear combinations. I'm going to do some experiments to see whether increasing the number of principal components used in training, what effect that has, and how many we actually want to use. On the math side, we think 3 will be enough. On the physics side, they think we should be looking at more like 40. So that would be an interesting discussion to have when we have some more results around that. So then let's have a look at those first 3. So on the left, you can see just the first 2 principal components plotted together, with the color bar being methane. So you can see the higher values of methane in the darker red and the lower values in the darker blue, and the kind of lighter blue and the lighter red or orange are those middle values. So on the left, you can see that there is a pattern. It's not a clear separation of the higher and the lower values, but it's not completely random, which means that there is some correlation between the 2 principal components, the first 2 principal components, and the methane concentration. It's not necessarily causation. This doesn't say absolutely the network will be able to work it out, but it's an indication that there is a correlation, and therefore we might be able to see some better results. And then when we look over at 3 principal components, it's hard to say at this angle, and I didn't twist it round. Maybe I should have done. Maybe we would have been able to see it clearer from another angle. But to me, it looks like we've got layers now. So the darker reds on the bottom and the darker blue looks like it might be on the top. It's important to also remember that the concentration of those darker blue points and the darker red points is much lower than the middle points will be. So you wouldn't necessarily expect a dark blue stripe or bunch. But yeah, this means again that 3 principal components, there is a correlation between the 3 principal components and methane concentration, which is great news for me. And hopefully that will mean that when I do some training on this new transformed data set that I have, I'll get better results, or at least quicker results. So we'll see. So then let's have a look at the results of the actual network, the one I described previously. So at the top, kind of towards the left, we've got our actual data, the figure we saw earlier. And bottom right, we can see what the network predicted. It's pretty good, but when you look at it by eye, there aren't many points that are different. In America, it's blurring together a bit. North America, it's blurring together a bit in the predicted, whereas there's some kind of cleaner, darker points. In the actual, that's kind of clear all over the place. If you find the darker red points and then you look at them on the predicted, again, they're there, but they tend to be a bit softer and not quite so prominent. So that, I mean, as a baseline, this is a good result. We've got our training error of 15.97 root mean squared error, and our validation of 16.23. So all of those 3 sets give us a 0.73% error, which sounds really good. You think 0.73%, that's tiny, but unfortunately, in the Earth observation scientists tell me that if you have enough information and you are an expert in that area, you can, by location and time of year and a few other little bits, you can kind of guess to within about 10 to 15 parts per billion. So on that basis, 15 isn't amazing. It's very good. And in certain parts of the globe, we look at much smaller errors like 0.1, 0.01 even in certain points. Like Australia is pretty good. And then in other parts, we have more like 2, 3, 4, 5% error. So it's not quite as black and white as 0.73. So there is some work to be done, particularly on those extreme areas. So then just another example of how we look at these results. this is a density plot. This shows us we've got our actual methane or retrieved methane along the bottom on the x-axis, and then our predicted on the y-axis. This is ideally, you would just have a nice red line, or mostly a red line with a little bit of a blue halo along that straight line in the middle. The red shows us that there's a lot of points, a lot of data in that area, and the darker blue is where you've got a bit of or less data. So obviously, ideally, we want that nice red in the middle where most of our data is, and then the blue still within that line. It's not bad. The shapes there, it's this kind of left-hand side of the plot that is worrying, I would say, or the worry, or the improvements that need to be made, where we have the network is clearly not predicting things below really 1750. You don't see much of the network going below there, whereas we can see that there is data in that area. So that low extreme, the network's not predicting particularly well. And again, it is getting some of the higher points, but there are some higher points that have made their way over to the right. So the extremes are the problem. In terms of the real extremes, the lower extremes are the problem. In terms of the majority of the extremes, you can see that this higher, below the line at the top, we've got quite a lot of bunched up data. So there are some improvements to be made at the extremes. There's also some improvement to be made in that middle bit where you can see a slight singularity where it's a bit green between the red, which is something that needs investigating. So I need to investigate whether that is to do with the fact that there's not that much data there to have a high concentration, or whether, as it looks like, because you've got that kind of fanned out line there, there's something going on at the 1850 mark that it's not predicting so well. So yeah, those are the results, and we're relatively pleased. My next steps will be to look at potentially a regression tree, which would pull out some of these extreme points and build networks individually for those extreme points. So the majority of the data does well with this, and then some of the data would be pushed off to other networks. That would involve some classification probably, or k-means to get some clusters, which I've loosely started working on, but don't have any strong results to share at the moment. And then potentially some error correction techniques that I've started to look into would be another way to go. That's my last slide. I'll just quickly mention the technology things that I use. So most of my work was done using Python, and I use Keras and TensorFlow for the machine learning things. I use a little bit of Jupyter Notebook and Atom for the coding itself. I think that's it. I think that's everything I use. And the HPC at the university for the handling of the large data. I thought I had a slide that said thank you, and I'm open to any questions, but apparently I didn't include it on this deck. So thanks very much for listening to me and having me, and welcome any questions.
Thank you very much, Rose. We have a few questions in the chat. Maybe people would like to unmute themselves, or like if you would like to keep it in the chat.
I don't know how to see the chat while I'm sharing my screen, which is maybe a problem for me answering questions, but yeah.
Okay, I can read them. So Ying is asking, how do you decide the number of hidden layers and the number of nodes?
Okay, so it's mostly trial and error, to be honest. I had a few, as I said, I had a couple of papers that I'd seen where they'd done a similar thing with carbon dioxide. So I used that as a starting point. And then I added and removed layers until I got to a point that I was happy with. And the same thing with the number of nodes. I had a base starting point from a loosely connected or slightly similar project, and then just tweaked it from there, really. I don't know if that answers your question, but yeah, it's mostly trial and error, to be honest.
Yeah,
With some,
yeah, okay, I can understand that.
Yeah, with a little bit of educated guessing.
As is nearly everything in science, in engineering, educated
all right,
guessing.
that answers my question. Thank you.
Okay, thank you.
There is another question here from Muhammad. Maybe you would like just to unmute yourself and ask the question yourself. Oh, I think they're not here. Okay, let me read it. Okay. Do you know what would have happened if you had input the raw input features and no PCA at all, and instead maybe used an extra layer in your network architecture, and whether if you had visualized the embeddings after the first layer would have been more or less beneficial than PCA?
Okay, that's an interesting question. So the results that I have shared today are actually without PCA. So what I don't know is whether with PCA it will be more efficient. In theory, yes, PCA kind of would hopefully reduce the size of the network, because the network will in some ways do its own PCA at the beginning, first few layers. So yeah, that's a valid question, but I don't have an answer because I don't have the results with PCA to compare to. He's not here to say whether that answers his question, is he? Okay.
Doesn't appear so.
Okay.
Do we have any more questions, or can we proceed to the second presentation of our evening?
Can I have one more question right after Mohammed's idea about this adding extra layers of PCA? I was wondering what kind of difference would it make if it's extra layer to build up 3 nodes instead of using a PCA or extra like several layers to build up 3 nodes and then follow your other neural network architecture, or you just use a PCA to create like 3 features and then feed it into the same neural networks. That's kind of question. I wonder, would that make a difference?
You cut out a little bit, but I think I know what your question was. I don't know if that was me. I think it might be my internet. So you can, yeah. So the hope is that the PCA will help the network, because in theory, while it's training without PCA, the network would be able to work out these linear relationships, and you may need more layers, or you may need to train for longer. So doing the PCA ourselves and then inputting it to the same network or even a smaller network with less nodes and that kind of thing, in theory would help kind of giving the network a helping hand, finding those linear relationships so that it can see the more complicated relationships. But also if you've got 1800 features going into 200 and whatever I said, 56 nodes, that's each of those 1800 features has a weight and a bias at each of those nodes.
Yeah.
So in terms of the network, not doing PCA increases the number of weights and biases and the back propagation and all of that, and the time that takes massively, and it's not a very difficult or slow process.
Okay, I understand.
Before. So in that respect, if it works and if it produces accurate and potentially better results, then it makes sense to do that rather than to try and build a network that does it internally. Yeah.
All right, thank you.
Any more questions? Going once, going twice. And I believe sold. Thank you very much, Rose. That was amazing.
Excellent. Thank you.
Thank you.
I'll stop sharing.
And I am happy to introduce our second speaker of the day. And I apologize in advance if I'm mispronouncing your name, because I haven't had time to check in advance. So our second speaker is Elias Volta-Georgis, who is a second. Oh, so
yeah,
I guessed it right. Cool. So Elias is a second-year PhD student at the University of Leicester, and he's interested in addressing the shortcomings of data-driven artificial intelligence systems. An amazing topic, if you ask me, and super important. Thank you.
Let's see. Okay, can you see my screen? Let's just see, and then you can hear me as well, yeah?
All good.
Okay, perfect. Okay, so yeah, so my name is Elias. I'm second year PhD student at the University of Leicester. So I'm going to like third year now, just finished my second year. So my main work is to sort of understand or to sort of like kind of give a good explanation of like the shortcoming of like data-driven artificial intelligence systems. So things like why do they, for example, fail to detect certain aspects of the problem you're trying to solve? And also like, is there any like majority security flaws within those systems? And like, can we actually understand the shortcoming of those systems and like trying to improve them, as well as like come up with like robust and trustworthy AI systems? Because like going forward, these systems are going to be applied in a lot of areas. I will mention a couple of here. So I think like, I don't know, facial recognition, health, and so on and so on. So like it's quite important to understand like when those systems are, the strength and the weaknesses are, and how we can make them more better and robust overall. Okay. All right, so the outline of the talk, so like I'll give an introduction of like what is artificial intelligence is, give like good definition from like a statistical perspective. So I'm not doing anything to do with like data modeling. I will define what is AI is from the statistical perspective, and gives us clear idea of where we're trying to go, and also like maybe clear out a lot of confusion. And then I will explain the second flaws, which is the adversarial example. So there's when you have a system where you perturb the input space, or you add a little bit of noise to the image or the input space you're trying to do, and how that change the behavior of your system. And the second thing is the new sort of attack we came up with, which is like a stealth attack. This is what happens with you perturb the entire network of the system, and what happens. And can this actually like give us an understanding of like why those systems are sort of like fragile against adversarial attacks? Okay. Right, so let's start with the introduction. So just quickly before I say anything, when I talk about like intelligent systems, what I mean by this is I'm not talking about like, for example, your capacity for logic or planning or emotional knowledge or creativity or your problem solving. So I'm going to use definition when I say intelligence, I mean the ability to accomplish a goal, right? So this is like when you have when I say I have an intelligence system, I mean is like there is a system that can accomplish a really defined goal. For example, my goal could be to distinguish the difference between cat and dogs, right? So that's my goal, is predefined. We know it, and when the systems achieve that, then we know that the system we say oh, it has intelligence. Okay. Obviously, if you follow the news, you know that the rise of deep learning, they have huge application when it comes to like facial recognition. This is when if you have like a smartphone, right, you can use it to sort of like for security reasons, for example, to identify people, and also to go through like buildings and stuff that they've been applied, or even airports, right? So like the passport checks, e-passports and stuff, they use facial recognition to identify a person. The other thing is healthcare. So like this is huge news now at the moment. It's like, for example, like identifying early detection in cancer, how protein fold, this kind of stuff that have major breakthrough now, especially like, for example, when it comes to like even cancer, like breast cancer, early detection, and so on. Obviously, the other major thing is the self-driving cars. Yeah, you know, Tesla, all the news you hear. So like we are at the point where now level 3, which is like we can sort of like cars can obviously drive themselves, right, on highway, parallel parking, and so on and so on, for legal reasons, because here is where you have huge amount of document, right? It's very costly to, for example, that to use human. What you do is like you apply the systems, and they can go through like 100 years of history and then come up with a perfect strategy or good legal argument you can think of. Right. Okay, so like now I just talked about like obviously the application side. Now I just want to define what the problem is and like so how the one approach, how one goes about to solve this problem, right? So like I just want you to think about like from the just a framework perspective here. It's like, let's say you have input, which is your X here, and you have some output, so you have some black box, or let's call it nature in this case. It generates some sort of distribution. We don't know anything about that distribution, and we get some Y, right? Things like, for example, like I have like an image of a cat, and then I put through the sum system, and I get the answer cat, right? But there's no, I don't have any clear idea of like how to model a cat, right? So the question is like, how do you answer this question? So if you go about it like from the statistical perspective, like which is like statistical modeling, where you're making some assumptions about the geometry of the cat face, and you're trying to sort of like approach it from that side where you make an assumption. So we know that from obviously like from studies and stuff, those assumptions sometimes is wrong. They don't generalize really well. Then we move to the second thing, which is like now AI, which you do is like, and instead of like trying to define what this distribution is or what this nature is, what we do is like you have the data, you have label on the data, and you just like, okay, you have this black box where you put the input in, and then you have an output, and it gives you some sort of really good representation. Right? So if the way the system sort of like put together is like, so you have a data generator, right? So this is like my data will comes in, and I have some sort of supervisor, so like I'm trying to learn the supervisor, which is the S, and I have output Y, and what I'm trying to do is come up with like some sort of a learning machine where this will like kind of replicate this supervisor's attitude, right? So like I'm learning its behavior. As I see more example, obviously my sort of generalization will increase. Yeah, so this is when you're learning from the data, right? So this is the framework I'm working on. So like, this is how I define my learning, right? I'm not defining in any other ways. And so for more details, obviously, like please consult this with the reference there. Right, obviously, so yeah, like again, let's start with the data. So like, if I have, for example, like X1, Y1, which in the case, like if I have a data and the label, that means I'm working on in a supervised setting. So that means I know pretty much my label is predefined. If I don't have any labels, for example, if I just have the data and I'm trying to work out what that data is, that's when you have like unsupervised learning. And when you have like a mix of like both label and unlabeled data together, you should have like unsupervised learning. And obviously there's like different frameworks for different things. For example, like planning, you use reinforcement learning, but we're not going about that. But I'll just give you a flavor of what it is, right? So yeah, I just quickly will define what the statistical learning is from like supervised perspective. And then I will show you like how to sort of construct adversarial attack and stealth attack on that system. Okay. So like, don't worry about the maths too much, but so like when you have supervised learning is where you have some sort of like probability distribution where you don't know anything about. So this is your probability space P. I have samples from them, but I have no idea of the entire structure of their distribution. And what I'm trying to do is trying to learn this by sort of like imitating, right? I have a measure, so like because I have the true label and I have a label I think is true. So like I can measure the difference between those 2 points. So that means like I know but I know my error. I know how far away I am from the true label. So and I define this expected risk, which gives me some sort of measure using this loss function. So this loss function measures the distance between y and f of x w. So that this is my true measurement of like how far I am from the true label. And what I'm trying to do is I'm trying to minimize this. I'm trying to get close as possible so that I have 2 points that are identical. And yes, obviously given those data samples, right? So I have n number of data points, and I'm trying to approximate this distribution using this framework. So again, so like you make, sorry, let's go back. So you make an assumption that your data is IID, meaning it's fixed. those any given two data points are independent. So that means that you can do, you can say that you can approximate this reasonably well for a given time. But P is fixed again, so the distribution doesn't change, right? The label stays the same. So, but it's unknown. I don't know anything about it. So I'm trying to learn this, right? And so the majority of problem are framed in this way. And again, so like if you solve that problem really well, you do have a success, right? So those are the success that I talked about, which kind of gives you a feeling of like, if you successfully solve those problems, you can have a really good understanding of what's going on. But again, you still don't have a really good understanding of why the systems work, right? So majority of the explanation you have is based on the behavior that you don't really have a control over, because like what you're assuming is like the samples is fixed, right? But they're not, and then the IID, we know they're not. So like you're making those assumptions so that like at least you have some sort of like the problem is not too complex so that you don't approach it. Like, so if I say that the distribution is not fixed, right, I have to compete forever, which you don't have that there. Okay, so any questions so far? No? Okay, so let me go on. Yeah, so Rosie mentioned a little bit of like deep learning. So what is the deep neural network? So you have d-dimension of inputs. So like I have a little picture of here, all right? So you have n number of layers. So for example, if I fix L to be 1, that becomes just normal neural network instead of being deep neural net. N represents your number of neurons, and you have alpha here, so just your activation function. And you have an offline layer that are fixed in the dimension. So and then you pile them together, you stack them together one by another, and you have really complex function that represent has really powerful representation power of any given function. Okay. All right. So for example, like this is AlexNet. This is the first one sort of like uses like convolutional neural net and with deep. With a dense layer of 2480, and can classify 1000 class, right? So you have an image, so you do some sort of like a transformation. Those are like max pool and convolution. So they don't, they just sort of like, so here is your understanding the pixel representation, but the actual computation you're doing on the neurons. So like, and today, sort of like the talk, sort of like especially stealth attack, is the attack on specifically on the neuron set of the architecture, right? Anything else? Okay. Right. So the question I'm trying to sort of like ask is what happens if you sort of like some sort of perturb the image, and what happens, right? The question you're asking is like, okay, let's say I have an image of like I don't know, a cat again. Is you add a bit of noise, and can my system correctly classify that after you add this bit of noise? Okay, so what is adversarial example is like, again, is the idea is just to add a small perturbation to the input image. Sorry, this is misspelled here. But so you have a target. So this attack can be target or on-target. So I can target a specific image and perturb it in a way that is the way I like. So meaning that when you have a targeted attack, so for example, if you have a classifier, so for example, here you have a classifier of panda, you can clearly see that, like, for example, you add a bit of epsilon plus noise, and you mix them together, and then you input to the system, and also you can see that the system misclassifying this as obviously not panda with 99.3 confidence, right? This shows you like the system is very unstable in essence, like a little bit of noise to the input is doing a great damage, right? So that obviously for more details how to sort of implement the system, please again, so like check the reference. Yeah, so the framework of adversarial example is just this. It's like you have an input, you have epsilon, and then you add noise to that image and see what happens to that network. And the majority of the systems are sort of like very vulnerable to this kind of attack, and they because of the complexity of the network itself, they're very vulnerable, and there is no like a defined framework or mathematical theoretical explanation of why this stuff happens. And we need to sort of like obviously understand this, because imagine if you have facial recognition system that is sort of like a security, right? And somebody puts, I don't know if you have a smartphone or not, you can just wear a mask and then trying to recognize yourself, right? Although that's yourself, like the phone doesn't recognize that, right? So it shows you like the seriousness of this kind of attacks, and they can be used in a very targeted way, meaning that like you can have an AI system. So if a person looked at this image and be like, oh, there's a panda, and it looks to that image afterwards as well, after applying this noise, it looks, for the person, for a human being, is very indistinguishable, right? Imagine a security person who's like using this kind of networks, and you show him, I don't know, your fake ID, that sort of the systems gives you, classifies you as the person, the correct person, although you're not. So that kind of stuff is major concern, and it's like we need to obviously understand them and why they happen. The other thing, this is the one of the, so this is when you have like physical perturbation on input. So this is like, imagine you're on a self-driving car and you see like a stop sign. What you normally do is you'll have an input and you'll add some sort of mask to that. Sorry, you add some sort of mask to it. So meaning that you physically perturb the image, or you add like plaster or some sort of graffiti that is not visible to, I mean, it's visible to humans. So like humans will look at this and they're like, oh, that's a stop sign. But what the car sees, it's with after neural network is telling you, like the system says, oh, the speed limit is 45, right? So and the stop road sign, you actually, the system's telling you to go after applying this. As you can see, it's like it's very difficult for anybody to look at this and say that, oh, that's an attack, right? You look at this and you think, oh, this is a stop sign where you normally stops, but the car would actually accelerate. Yeah. So again, this is when it's physical, not just an input image, right? And again, for more how to do this kind of things, it's like you can please look the reference. Okay. All right, so stealth attack. So what I've described so far is you have image, you're sort of like I don't think of it like you're shaking the image, right? So you're adding a noise to the image. So the question I'm trying to ask, or what we did here is that what happens if you perturb the network itself? So like, but you know, like for example, like the talk previously, like you have 2 layers, right, with different number. What happens if I pick one node of that layer and just like perturb it or change the structure, see what happens? And if I do change the structure of that network and it sort of come up with a similar behavior to like what you happens in an perturbed image or adversarial attacks, then I know that some sort of like I have some sort of awareness of what's going on, right? And the question is, by sort of like answering this, you can answer really fundamental question is like why the system is very vulnerable against adversarial examples, and is there any fundamental reason why they occur as well, and then how can you exploit them? So in that sense, like how can you make your system more robust by actually understanding this? And then the other thing is like, is there a unified framework which might kind of help you understand how perturbing the image as well as the network architecture sort of like gives you better understanding of like why this system affected and actually what the system actually is doing as well. So like you understand the decision boundary or the limits that system can take. And I've actually having got a good understanding of this, not only like kind of, you can answer a question like, can I come up with robust system? Can I come up with more trustworthy or certifiable system that is like, I can verify that from consulting by different methods, my system is more robust against different attacks. All right, so the problem so we're trying to solve here is like, you consider you have a classifier. So like we don't really care now how you'll come up with this. This can be classifier or can be any intelligence system, like I said before. And then you have a verification set with inputs that you test your classifier with, which is unknown to me. But what I do know is that I know the number of sort of verification sets. So I don't know your exactly your data point, but what I do know is I know the structure of your network. So what I'm trying to, so what I'm trying to do is I'm trying to modify the classifier or your network structure so that I can achieve the behavior I want of the system. So this perturbed structure is unknown to the developer, right? So for example, let's say you have an AI system that can distinguish between, I don't know, like let's say in a hospital settings, like with a cancer patient and a non-cancer patient. And I don't know how sort of like the exact detail of your data set, but what I do know is I know the structure of the network and I know the number of sets you have. So what I'm trying to come up with is perturb that network, so a different change of behavior, so that is there should be less than epsilon here. The distance between those two actual network and the network I perturb is very small and is distinguishable to the attacker, the developer, sorry. And what I'm doing is like I'm creating a new data set. So this is X bar here that is malevolent. So if I put that data in the system, then I know that I achieve a behavior I want, but is unknown to the developer. So that's the problem I'm trying to solve here. So more of kind of diagram to explain what's going on is like, so you have a validation set, which is unknown. I don't know anything about it. And you have test outcome, but I do have an idea of like what the system is doing. What I'm trying to come up with is an input, right? That puts in the system that's alter the outcome. So right, what I'm trying to do is like generate input that is like has an original structure to the data set. So like if I show you an attacked image, you wouldn't see or you wouldn't distinguish the difference. Yeah, but I think, is that clear? Hopefully it is. If not, please ask the question afterwards. Yeah. So here's an example. This is one of the attack we constructed on, for example. It's not very deep in the network, but like think of like let's say you have 100-digit data sets, yeah, like 0 to 10, sorry, 0 to 9, and you have a network. So like the image input is 25 by 25, and you have like let's say 15 layers, not a lot, but the last layer is fully connected layer with 10 neurons, and you have softmax at the end. So like what I'm trying to construct the attack is like I'm picking one node from the final layer, 10 layer connected, and I'm gonna sort of change the structure of the output. So I'm modifying then one node so that it alter the behavior of the entire network. Okay, I hope that's clear. So here's an image. So like you have inputs so from let's say 0 to 10. Here, what I'm trying to do is I'm trying to come up with one new neuron that is not detectable by the developer, but like obviously it's detectable by me. I'm controlling it, and when I input those node to the system, it alters the behavior of the entire network. Okay, I hope this is clear. And here's an example. So for example, like you pick number 7, and you'll come up with, so you pick the layer of the output layer at the end. You calculate this value. So like this node, again, so like for how to sort of like calculate this node, yeah, again, just visit the paper. There's more information there. And what we're planning to do is here is like, obviously the system see number 7, but the output's actually number 1, right? You see that, so like now I have full control of like the behavior of the system. So like the system sees 7, but obviously with this node helps, the output is 1. Yeah? So that's the structure of the salt attack. And what you're doing here is that you're perturbing the entire network so that you're not only like hijacking the entire network, but you're controlling the output of the system. And this is actually unknown to the developer and is very difficult to detect as opposed to adversarial attacks. Because adversarial attacks, you can become robust and by just training, right? You can just increase your training data set so that you include adversarial attacks so that your system more recognize adversarial attacks. However, it's very difficult to sort of like become robust at the network perturbation, because like I can pick a node that has or neuron that has low value or no significant to your system, and then I can sort of like make it more. I can make that point as my attacking, so that I construct my attack around less important neurons, so it is not undetectable to you. Yeah, so like the yeah, and yeah, probably that is my end of my talk. Yeah, thank you very much. I hope this is clear, and
thank you very much, Elias. That has been amazing and an incredibly important topic. Do we have any questions? Okay, we have some thanks in the chat. If you have a question, just go ahead and unmute yourself and ask it. Going once. Going twice. Okay, it looks like we do not have any questions, but I think you can reach out to our speakers directly after this event. Thank you very much, both Rose and Elias. And yeah, hope to see you again in our events.